Hi everyone, Mr. Sobolewski here, and in this video I'm going to be reinforcing what Mr. Lucy was talking about in his video. So the Arrhenius definition of an acid, the Bronsted-Lowry definition, conjugate acids and bases, and strong versus weak acid and bases. And then I'm going to introduce naming acids, which is a fairly simple concept. We spent about 2 weeks on naming ionic compounds. Don't worry, naming acids will only take us about 10 minutes to go over. So let's start with the Arrhenius definition. So here's a little picture of Svante Arrhenius, and this theory was devised around the 1880s or so. And according to the Arrhenius definition, what makes something an acid? Well, an acid produces H plus ions in water. So if we take like one of our classic acids, one you probably know, hydrochloric, is HCl. If we make it aqueous, meaning we dissolve it in water, what's going to happen? Well, you're going to get H plus ions and Cl minus ions floating around in water. We would call this aqueous. So according to the Arrhenius definition, this is an acid because it produces H plus ions when you dissolve in water. So in other words, every acid by the Arrhenius definition is going to start with hydrogen in the front. There's a lot of compounds that have hydrogen like in the back end of it, like for example, sodium acetate. Which would be NaC2H3O2. But that's not going to form hydrogen ions. That'll form acetate ions. So that wouldn't be an acid. What makes something a base? Well, it produces OH minus or hydroxide ions in water. So what that means is you really have anything in the front and hydroxide in the back. So for example, calcium hydroxide. Now, calcium hydroxide is a solid, but if you were to take that solid and dissolve it in water, make it aqueous, and I'm pretty sure this actually shows up as solid on your solubility table, but really when something's solid on the solubility table, if you heat the water up, which you guys learned in your molarity PhET lab, you can actually dissolve that in water. So if we take our calcium hydroxide and make it aqueous, what are we producing? Well, you're going to get Ca2 plus ions floating around, and you're going to get OH minus ions floating around. Technically, you're going to get two of these. So notice we produced hydroxide by dissolving my calcium hydroxide in water, which makes calcium hydroxide a base. Now, this definition worked for a good 40, 50 years or so, but people started to realize, there are certain liquids, solutions that are definitely bases or definitely acids, but they don't really fit this example. One famous example of that is ammonia. This was mentioned in the other video. So ammonia is NH3. And people have known ammonia is a base for hundreds of years before they really understood the chemistry of it. They didn't understand that it was one N and three H's, but they knew this ammonia acted like a base. So once we discovered that it was NH3, this was a problem because according to Arrhenius, a base requires hydroxide, but there's none here. So what this led to was an expansion of the definition of an acid and a base. So no longer does an acid have to have H plus in the front and a base have to have OH in the back. Here's the modified definition of an acid by the Bronsted-Lowry definition. Here's Johann Bronsted and Thomas Lowry. So according to this definition, first, an acid is going to be a proton donor. And here I said proton, aka H plus ion. This was something mentioned in the other video, and it's worth reiterating here. If we take a hydrogen atom, H atom, what is a hydrogen atom? Well, it's got one proton in the middle. It's got 0 neutrons. The vast majority of hydrogens actually have no neutrons. When they do have a neutron, they're actually incredibly unstable and radioactive. Most hydrogens have one proton, 0 neutrons, and 1 electron, which I'll represent as that dot there. So that's a hydrogen atom. 1 proton, 1 electron. Well, how do you turn a hydrogen atom into a hydrogen ion? Well, same way you turn any atom into an ion, you adjust the number of electrons. And to make an H plus ion, what do? Do we add an electron or take that one away? Well, we're going to take that one away. So look what happens when the electron goes away, forming an ion. Look what we have left. Literally just a proton. So that's why the term proton and H plus ion are interchangeable, because an H plus ion is just a proton. So anyway, according to the Bronsted-Lowry definition, acids are proton donors. So what that means is anything that gives away an H plus or a proton is considered an acid. And look at bases. Bases are proton acceptors. also known as H plus ion acceptors. So anything that accepts an H plus can now act as a base. And this fits our our model nicely because, for example, if we have NH3, ammonia, and we add an H plus to that, imagine an H plus comes by, or a proton, and it bonds with that. Well, what's going to form? Well, now instead of NH3, it's NH4, and it was neutrally charged. If we're going to add an H plus, our new charge is plus. And look what we formed. You should recognize that. That's ammonium, which is on your polyatomic ions list. So notice that ammonia can act as a base by accepting a proton, turning into ammonium, and this fits the Bronsted-Lowry definition, even though it wouldn't fit the Arrhenius definition. So those are those two definitions of acids and bases. This leads us into the concept of a conjugate acid and conjugate base. Basically, an acid can become a base after it does what acids do, which is donates a proton. After a Bronsted-Lowry acid donates a proton or H plus ion, it is now able to accept a proton. Think of it like you're holding a beach ball, and that beach ball is like your extra H plus ion. You can give that away. You can toss it to your friend, and that represents you being an acid. You're giving away an H plus. Well, what's in your hands now? Nothing. It's almost like there's a hole that can be filled. So your friend can now pass that beach ball back to you, turning you into a base. So think of it as you give away an H plus, and now you are able to act as a base because you have that opening. The term we have for that is a conjugate base. In other words, a Bronsted-Lowry acid turns into a conjugate base after it donates its proton. So by acting as an acid and giving away a proton, you can now accept a proton back, which means you can be a conjugate. Think of this like a potential base. Similarly, a Bronsted-Lowry base accepts a proton. Picture your friend catches the beach ball. Okay, your friend just acted like a base. Well, now your friend's holding a beach ball, and your friend can pass that beach ball back to you. So your friend, by accepting the proton as a base, now can act as an acid, and we call that a conjugate acid. In other words, a Bronsted-Lowry base turns into a conjugate acid after it accepts its proton. So there are these conjugate acid-base pairs where the acid will then become the conjugate base, and the base will then become the conjugate acid. Let's go through an example. So these should look similar to the ones in Mr. Luce's video. So on the left side, actually I should make these arrows double because they can go backwards. Actually, the more correct way to do it is like this, where you go with half the arrow there and the other half there. So in my top example, just finish this. All right, we have HCO3 with a minus charge plus water leads H2CO3 plus OH minus. So on the left side, we're going to identify the acid and the base. And on the right side, we're going to identify the conjugate acid and the conjugate base. The way Mr. Lucy did this was to compare, look for the pairs. Like notice HCO3 and H2CO3 are clearly like siblings. They're very close together. Now, which one is going to has more hydrogen? That's going to be your acid. Now, on this side, we're always going to have the conjugates. So this would be your conjugate acid, and this would be your base. Now here, the water, the H2O and the OH, those are like a pair as well. Which one has more hydrogens? That's going to act as your acid, and that's going to act as your conjugate base. So that's one way of looking at these. Here's another way of looking at these. What is a Bronsted-Lowry acid? Well, it's something that donates a proton. So looking over here, I want to think which one of these donated a proton. Well, how do I know that? I need to look at what they turned into. So notice my H2PO3 turned into HPO3 2-. What must you have done to go from H2PO3 to HPO3 2-? You must have given away a proton. Remember, a proton is an H+. So this goes from having 2 H's to having 1 H. It must have given away or donated a proton. What is a proton donor? An acid, which makes that my acid. Now looking at the water goes from H2O to H3O+. What must it have done to get there? Well, it must have it gained an H, right? And it didn't just gain an H, it gained an H plus, which means this accepted a proton, which makes that my base. Now in this side, my acid turns into my conjugate base. My base turns into my conjugate acid. Okay? So whether you use the just comparing whichever one has more H's is the acid, or if you think about what they did to get there, either way you can identify your conjugate acids and bases. One last thing on this slide. Notice in this top example, my water acted as the acid. In my bottom example, my water acted as a base. Do you remember that vocab term from Miss Lucy's video? Amphoteric. Something that is amphoteric, let me write that a little more clearly. Amphoteric. Something that's amphoteric can act as either a Bronsted-Lowry acid or a Bronsted-Lowry base, and water is a famous example of that. Sometimes it can accept a proton and turn into H3O+. This has a special name called hydronium. You'll learn about that later. Or it can give away a proton and form hydroxide. So that makes water amphoteric. Okay, last thing I'm going to cover in review before we do naming is strong versus weak acids and bases. So in terms of definitions, a strong acid or base fully dissociates into ions in water. A weak acid or base only partially dissociates into ions in water. Now this term dissociates really just means splits up into ions. So for example, we say HCl, when you put that in water, it's going to form H plus and Cl minus ions floating in water. There's another example, and I'm kind of out of room here. Let me just write it down here. I'll cover that in a sec. HF aqueous, which we're going to learn as hydrofluoric acid, produces H plus and F minus ions in water. But here's the difference. One of these is strong, one of these is weak. And what it means, in this case, the HCl, hydrochloric acid, is a strong acid, which means 100% of the hydrochloric acid, the HCl aqueous, is going to split into these ions. So at any given time, when you make hydrochloric acid, you will see 100% of it as H plus and Cl minus, and 0% of it as HCl still stuck together. If we compare that to a weak acids only partially dissociate, meaning at any given time, some of your HF is going to be split up into these ions, and some of your HF is going to be stuck together still as HF. So really the difference is how well can this anion rebond with the hydrogen. And you might say, well, why wouldn't it always do that? Well, there's something else in the solution that it has to compete with, and that's water. So basically, in this case, the water outcompetes the chloride in getting back the hydrogen. It's able to keep these apart. Where in this case, the fluorine is able to fight the water and take the hydrogen back. So let's look at what this would look like in a picture here. So a strong acid, a classic example of a strong acid is HCl, aqueous, and a weak acid is HF, aqueous. So in water, if you were to put HCl, you would end up seeing H plus, Cl minus, H plus, Cl minus, H plus, Cl minus, and you would see your waters kind of, surrounding these ions this way. Well, what would HF look like, a weak acid? Well, some of this would still split up, and you would have H plus and F minus. But a lot of it, in fact, most of it would still be stuck together. You would have HF still stuck together, HF still stuck together. Now, ions will, the waters will surround them, the ions in this direction. And we don't really want to show ions preferentially pointing any way towards these, so we can just show them like aiming sideways at them. They're going to randomly go one way or the other. But really, your negative ions should have the legs of the water pointed towards them. The positive hydrogens should have these circles of the oxygens. But in short, the big difference is in a weak acid, you're going to show some of them still together and some of them split up. In a strong acid, you're going to show all of them split up. Now, just doubling back to this point here that was made in Mr. Luce's video, strength does not equal concentration. In everyday language, if you were to let's say we're making a drink like Kool-Aid or something, or hot cocoa, and you're saying, oh, that's really strong. What does that mean? It means you put tons of that powderized sugar in the water. It's really concentrated. In acid speak, we don't use that same everyday speak. To say an acid is strong is not to say it's very concentrated. Certain acids are simply, by their definition, by their chemistry, strong acids. In fact, I'll show a list on the next slide. You can have an incredibly dilute strong acid that's essentially harmless. For example, HCl is a strong acid. You can take 1 drop of HCl and put it in a swimming pool of water. It's so dilute you can easily drink that water and be fine. Please don't try this at home. However, it's still considered a strong acid because hydrochloric acid is a strong acid. HF is a weak acid. That does not mean it's not dangerous. It does not mean it's low concentration. You can have incredibly concentrated HF. In fact, if anyone ever watches that show Breaking Bad, I'm a big fan of that as a chemistry teacher, you'll learn the power of hydrofluoric acid in that show in season 1. I won't spoil anything, but it's an incredibly dangerous acid, one of the most dangerous acids there is, and yet it's a weak acid because the term weak does not correlate with concentration. On this slide, I'm just going to give you some information that you should write down. You might see like a Texas question just asking about strong and weak acids. There are generally 6 strong acids that most textbooks will kind of agree on. Some will include a 7th one, but these 6 are the ones that we really need to focus on. And we'll get to naming these afterwards. So the 6 strong acids are hydrochloric, HCl, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. So I just want you to write these down. There's no need to memorize these. Weak acids are all others, and there are thousands of them. But the most common ones you should recognize, and you will after you do the naming, are acetic acid, this is also known as vinegar, carbonic acid, that's present in water and carbonated beverages, and hydrofluoric acid. So again, there are 6 generally accepted to be 6 strong acids, and all the rest are weak, and these are kind of the very common ones. For bases, we mentioned what strong acids are, not really what strong bases are, but it's the same thing. A strong base will fully dissociate into ions in water. Most alkali metal, which are group 1, or alkaline earth metal, group 2, hydroxides are strong bases. Notice these all fit the Arrhenius definition of a base because they have hydroxide. So these will all fully dissociate into those ions if you were to dissolve them in water. Weak bases are all the other bases, and again, there are thousands. The most common one is ammonia. So ammonia is a weak base. Does not mean it's not dangerous. I mean, ammonia is a cleaning product, and it's famous for its incredibly potent smell. It's one that if you were to smell it directly out of the container, again, do not try this at home, it can cause severe brain damage. It's incredibly potent. Just because we say it's weak doesn't mean it's not dangerous or potent. Okay, and I've reached the last part of my video where I'm going to quickly talk about naming acids. Now, when we name acids, there are 2 categories of acids, which are binary acids and oxyacids, and they're named in different ways, so we need to understand these differences. Binary acids are 2 elements, binary, like the binary computer language, 0 and 1. It's only 2 options. So a binary acid is hydrogen and 1 other element, which is going to be a nonmetal. For example, HCl, HF, H2S, H3P. Now you might say, hold on, this is not 2 elements, or that's not 2 elements. Well, it's not 2 atoms, but these are 2 elements. It's hydrogen plus 1 other element. Now, how do we know how many H's go on the front of these? Well, you look up the charge of that nonmetal. So for example, Cl forms Cl minus, F forms F minus, S is 2 minus, and P is 3 minus. Hydrogen is plus. So when you're making hydrogen bonding with chlorine, it's 1 of these and 1 of these. Same here. Now for H and S, you need 2 H's and 1 S, and for P, you need 3. So these are all examples of binary acids. Oxyacids are hydrogen and a polyatomic ion that contains O. I want you to take a sec and find your polyatomic ions list. You'll notice that the overwhelming majority of these contain oxygen. In fact, there's only a couple that don't. So for oxyacids, you can really think of it just as hydrogen plus a polyatomic ion. But technically, it does have to contain oxygen. There are a couple exceptions, and I'll address those at the end. So for example, this is hydrogen bonding with nitrate. This is hydrogen bonding with phosphite. This is hydrogen bonding with carbonate. This is hydrogen bonding with acetate. And again, you could say, well, how do you know how many H's to stick on the front? Why do you have 1 here, 2 here, 3 here, and 1 here? Well, it's all about the charge. Nitrate is minus, so it gets 1 H. Carbonate is 2 minus, so it gets 2 H's, and so on. Oh, and by the way, if you're going to write this, you cannot stick that H with these H's and call it C2H4O2. You can't do that because it's very important for this acid, which you're going to learn is called acetic acid. It's very important to show that hydrogen in the front because that's what makes an acid an acid. All right, let's get into how we name these. So naming binary acids. Before I show this, I want you to think about HCl. You know how to name that one. You've probably been naming that one for years. What is HCl? Hydrochloric acid. Use that as your template. Hydro plus the root word of the nonmetal, in this case chlorine is chlor, and then ic acid. Hydrochloric acid. All right, so here's some examples. That's hydrochloric acid. HBr. I want you to speak to your computer right now and tell me what that acid's name is. Hydrobromic acid. Right, because it's hydro, the bromine becomes bromic acid. Fluor, hydrofluoric acid. Remember, fluorine is spelled F-L-U-O-R-I-D-E, not O-U. Iodine, hydroiodic acid. So the root word of these halogens, which is group 17 elements, chlorine is chlor, brom, fluor, and iode. Next one, H2S. You might say hydrosulfic acid would make total sense, but that's not what it is. It's hydrosulfuric acid. Just got to kind of remember that one. And for phosphorus, you might think hydrophosphic acid, but it's not. It's hydrophosphoric acid. But the basic idea here is these all start with hydro. They end with ic acid. So these are the 6 common binary acids you should know. Let's talk about naming oxyacids. This is different. The rule is this. Adic-itis. Sounds a little strange, but you got to remember adic-itis and no hydro. Here's one way to remember adic-itis. I ate too much, I feel sick, and a snake bite is poisonous. Adic-itis. Now, what does this mean, this weird adic-itis thing? Look at your polyatomic ions list. Notice with a few exceptions, these all end in either ate or ic. Nitrate, nitric, chlorate, chloric, or ite, I should say. Nitrate, nitrite, chlorate, chlorite. The 8 polyatomic ions become ic acids with no hydro. The ite polyatomic ions become us acids with no hydro. For example, HNO3. Okay, HNO3. That's hydrogen plus nitrate. This is called nitric acid because 8-ic, right? And notice no hydro. You don't say hydronitric acid. It's just nitrate becomes nitric acid. HNO2. NO2 with the charge of minus is nitrite. So this is hydrogen plus nitrate. So notice ite us. So nitrite becomes nitrous acid. Here's some more examples. Now, there's no need to memorize all these. If you remember the rule, you'll always have your polyatomic ions list. So there's plenty of ones that we can go through. H2SO4. What's this polyatomic ion? That's sulfate. Not sulfite, that's sulfate. So this is going to be, remember, no hydro. Sulfate is going to become sulfuric acid. And I know you might say, wouldn't it be sulfic acid? That would make sense, but that's, blame the IUPAC, the group in France that makes all the naming rules. All right, H2SO3, that's sulfite. So if, I forgot to make that small. If this is sulfuric acid, this one's going to be sulfurous acid. Remember, no hydro. H3PO4, H3PO3. What is PO4 with a charge of 3-? That's phosphate. And this is phosphite. So phosphate, ATIC, is going to become phosphoric acid. And phosphite is going to become phosphorus acid. Not to be confused with the element's name, which is phosphorus. Notice the very small difference in spelling. So oh, we got to be careful. So phosphorus acid is H3PO3. HC2H3O2. What polyatomic ion is this? That's acetate, 8-ic, acetic acid. So again, you take that acetate, you make it ic, acetic acid. CO3, that's carbonate. What's the charge of carbonate? 2-. That's why there's 2 H's here. And because it's carbon 8, this is going to be an ic acid, carbonic acid. And the last ones I'll go through are this group of CLOs. So you'll see those on your polyatomic ions list. This is hypochlorite, chlorite, chlorate, and perchlorate. Well, that's what the polyatomic ion is without the hydrogen. So remember, adic-itis. So hypochlorite is going to be hypochlorous acid. Chlorite is going to be chlorous acid. Remember, ite-us. Chlorate is going to be chloric acid, and perchlorate is going to be perchloric acid. And this one was one of our strong acids. Strong acid. Okay. So that's how we name these. Again, you don't need to really memorize many of these because the rules are the rules and there are very few exceptions. Now, what are those exceptions? If you look at your polyatomic ions list, you'll probably see just 2 that don't end in ate or ite. Well, 3 if you include ammonium, but that's positive. So Cn- is cyanide and OH- is hydroxide. Well, hydroxide is not going to form an acid when it bonds with H+. It's going to form water. So this one we can even just eliminate. You're not going to have hydrogen hydroxide as your acid. But this one can form an acid. What acid would that form? Well, it has a charge of 1-, so it's going to bond with H+ and form HCN, aqueous. Now, do we call this binary rules because there's no oxygen, or do we call this oxyacid rules because it's polyatomic? And the answer is we go with the binary. We're going to call this one hydrocyanic acid, not just cyanic acid. Okay, so that's kind of that one exception there. All right, so that's how we name, and I hope that the intro part of this video helped you understand the definitions and conjugate acid bases. Please join your teacher in Zoom or Meet if you have any more questions about this. Good luck.